Okay, these are problems I gave out in class. I think it was Friday. Um, I'm pretty sure it was Friday. Anyway, I'm going to go through these. These are on rotational dynamics, so like forces for rotating objects. The first one I did in class as a starter, and I've also done it on another homework, so I'm going to skip it. It was actually part of the homework week of 318 also. So you can look there if you need that one. All right. This one I did in class, and I know everybody was like, bleh. So I'm going to go through it. This is an Atwood machine. If we remember this from a long time ago, Unit 2, when we looked at this in Unit 2, okay, we've got a pulley. It's got masses hanging on either side of it. If one of them, if there are different values, different mass values, then this is going to accelerate when we let it go because this mass is going to travel downwards. This mass is going to travel upwards. When we looked at this back in dynamics, we assumed that we had no friction. We assumed that the string and the pulley contributed no mass to the scenario. And in that case, our tensions were the same. Now we're going to include the pulley. Okay, so we're going to include this as a rotating object as part of the scenario. That means these tensions are going to be different. So it makes the scenario, in a lot of respects, it's the same, but it makes it a little more complicated because now we're considering torque as well as net force. Okay, so if we think about net force, each of these have got an M times G, and then they've got a tension. Okay. Those are not the same, again, like I said, because now our pulley's got mass. And then we've also got torques acting by the tension pulling on the pulley. So this has got a torque in one direction and then a torque in another direction as we pull. Okay, so this is going to be, well, as this one pulls down, actually, I probably should have made my arrows opposite here. Trying to picture this as this side pulls down, it's going to turn in a clockwise manner, right? And then as this one pulls down, it's going to turn in a counterclockwise manner. All right. Okay, so we've got some information about this. We've got the mass of the blocks. We've got the radius of the pulley. We're not going to worry about friction, okay, but we are going to have mass. The pulley is contributing to the scenario. When released from rest, the heavier block falls 82.3 centimeters in 2.95 seconds. And what is the magnitude of the acceleration, okay, of each of the two blocks? They're still going to accelerate with the same value because they're all moving together. This is like a whole system. So for the first part, we're looking for linear or tangential acceleration. Okay. And so we're going to use kinematics to get that. We're not quite ready to use FNet yet, although we could use that. But we don't have really enough information to do that. So we're going to use, we've got a displacement equals, I'm going to just convert that to meters, 0.823 meters. We've got a time, 2.95 seconds. It's released from rest, so we've got an initial velocity. We want acceleration. So I used this equation. And there are times where you see combinations, okay, of kinematics and dynamics. We did a little bit of this back in the dynamics unit, where we used a kinematics equation to get something, and then that helped us get something else. So here's a displacement. This goes to 0 because I'm starting from rest. 1/2, I'm solving for A, and then time is 2.95 squared. Basically, I'll try and do this all on my calculator. 823 divided by 0.5 times 2.95 squared gives me 0.189 for my acceleration there. Okay. All right. So that's the first question. What's the acceleration of the two blocks? The second question, what is the angular acceleration? Okay. And this is where I said we can use our handy dandy bridge equation. Tangential or linear acceleration equals r times alpha. So these bridge equations are really helpful. Should be familiar with them. If I want angular acceleration, I'm going to take this that I just solved for, divide by the radius. So 0.189 divided by, let's see, the radius is 5 centimeters. I got to convert that to meters. So that's going to be 0.05 meters. And that's going to give me 3.78 when I divide that out. And that's going to end up in radians. Because this is meters per second, this is meters. So I'm going to end up with radians per second. Meters per second, sorry. Yep, and then meters. So the meters cancel, and I get radians per second. So that's really the answer to this one. I'm trying to save some space because there's more to this problem. Okay. Then we want the rotational inertia. Okay. And this is where it gets a little complicated because we've got to figure out what our net torque is. So we can solve for rotational inertia. We've got this value now. Net torque is going to be the difference between the tensions. Okay. So we've got a tension. Okay, let's see. I said this one was clockwise and this one was counterclockwise. So that means I've got T1 minus T2. I think that's right. One of them is going to be in a positive direction. One's going to be in a negative direction. Okay. And then if I multiply that by r, the radius, I would get my net torque. I don't have these tension values. Okay, so I'm going to go back to linear dynamics to figure those out. And this is where I said you can have, these have got forces acting, this system, there's forces acting in the system. There's also torques acting in the system. So we've got two different linear and rotational motion happening here. So back on our old way of doing dynamics, net force is mass times acceleration. If I want to get these two tensions, okay, then I'm gonna set up some F net equations. So for my first one, I've got mg pulling down. Oops. Make sure I didn't pause that. I've got mg pulling down, okay, and then I've got T1 pulling up. So T1 minus mg equals ma. This is for my little mass, okay. So then T1 equals ma plus mg. M for the smaller mass is 460 grams. So I've got 0.46 times my acceleration I already got, my linear acceleration up here, plus 0.46 times 9.8. And that's going to give me, okay, 0.46 times 0.189 equals that. Plus 0.46 times 9.8 gives me about 4.6 for my T1, 4.6 newtons. Okay. I'm almost at 10 minutes here, so I'm going to stop this one, and then I'll pick up with getting T2 and then finishing up these two in the next video.